from the sublime to ridiculous. You talk about stuff you can't talk about. This is all public domain. All the source code for this is sitting in GitHub repositories and everything else. Again, it's an active project. That's, you know, today it's worth, I think I put a number in it. It was worth that amount on the day we wrote the slide. I've no idea what it's worth today, okay? We don't track these things. Right. Let's move this. I know, I'm sorry it's a bit boring, we'll quickly go over this notion of what a blockchain is, but what's really interesting about this and why we were particularly interested and drawn to this problem is that the notion of safety and security of the whole system is intimately tied up with its ability to perform. Right? So if you don't keep this system live and keep it moving at a certain rate, basically its value disappears. At least in principle, and that's an interesting problem because, you know, that's a liveness problem. Right. So the key thing about the notion, and I'll quickly go through this, of a distributed ledger is that basically people are keeping the notion of a history. They're organizing blocks that get moved and changed. There's transactions that occur in those blocks. They are linking them with cryptographic checksums, and they are basically every time you add a block, you're making choices perhaps of which blocks to add because the front of the chain isn't safe, or there's a potential many possible futures you might be choosing from. But actually the fundamental proof is there's a genesis point way back in the past that you have a unique history back towards. Okay. Now, the interesting thing about this particular system is that there's a lot of hype around these systems, but this one's got, it's the first proof of stake algorithm that's got an accepted proof, mathematical proof from people in the University of Edinburgh. Basically, it's a hell of a lot more computationally efficient than proof of work systems in the sense that the planet could survive while actually doing this, whereas, you know, the proof of work systems are basically turning greenhouse gases, as was so nicely described in Hitchhiker Guide's terms earlier, you're burning the trees to preserve the value of the leaves in a proof of work system, right? And yes, it was worth whatever that was on that day, and it's funded by RHK. Right, so here's the nice, interesting challenges. You need to diffuse the data that's inside this system to nodes around the world in 20 seconds. Okay? The topology or the actual path that your data takes isn't necessarily related to the physical topography of the world. They can go across the world several times, and there are various attack scenarios. We are making the assumption under a lot of these processes that there is a presence of adversarial actors against the system. So we have to basically make sure that under a large selection of active adversarial acts and large-scale disruption to world telecommunications and computational power, this system can still progress. All of these systems are making local decisions that they are checking effectively. They're trusting other people because they make the same decision. Does that make sense? You're getting a block from somebody else, and you say, I believe this block because I can quickly do the cryptographic check, and I now believe that this system is a valid extension of the previous blocks for various reasons. And the issue of high assurance. But it's a fast-moving game, right? You can't afford the years to do formal proof. You've got to try and get as close as you can, as fast as possible. And the people we're working with, IOHK, and the people we're working with, we're trying to do the best we can with semi-formal approaches. Whereas if you look at one of the other ones that was launching last week, it was the result of 200 people writing the code with nobody actually in charge, and no one taking any. I don't know. Now just work out if there's any bugs or any Trojan horses in that code base. Right. Verification goals. We're obviously trying to make sure the system progresses. We're trying to make sure that it's got no faults inside it. And we're going to talk a bit about the issue, and there are we've done that pretty well for the core, and there are issues to do with things like user wallets and other things that are important as well, which we will just touch upon shortly. We have basically been looking at how do you model the attacks against this system, right? And how can you ensure that you have got reasonable certitude, if that's the right word, that you can handle the potential set of adversarial actions. And I know it's impossible to have a complete reasoning about that, but you're trying to take reasonable ideas. And again, you're having a massive idea that there's a huge social pressure to deliver good service to everybody anywhere in the world. Yeah, not a small problem. Again. One of the interesting things I picked up from this morning is that we still don't know how to capture requirements. Basically what we're saying is, and we've tried to introduce this notion of an intentional semantics. What did you darn intend? Can we capture your semantics, please, your intention? Fortunately, there's a bunch of mathematicians at the top end of this process. So, the notion of a proof, the notion of set theory, and the notion of statements that you can, lemmas and proofs, or things that we can use to interact with those people. And that's really useful. So we find mathematics is our communication tool at the top level of this process. And what we're basically going to say here, I will talk a little bit more about formalizing how wallets behave, and because actually it turns out making the core work we've done, making the wallets performant is an interesting issue. We have done a large amount of work on this issue of, will this stuff remain performant over time? There are still some issues to be done to do with various ways in which certain aspects of data structures will over time grow, and will they actually stay bounded over time? And actually there's very current work going on about how we construct the game theoretic semantics for the incentives of how you actually do things, so that it is in people's best interests to actually do the right thing individually for the collective whole. Like, hey, social engineering on a global scale here, assuming that the actors in this process are not too myopic. If you've got any interest in game theory, you'll know that you have this idea that people act in their long-term interests is what game theory is based on. It turns out humans don't work that way. They often act in their short-term interests, but you're hoping there's not too many of them that are going to be that myopic. Basically, how do we resist DDoS attacks? The internet, actually IP is one of our main problems here. And if any of you have ever started to try and look at systems that have points of contact with the outside, with the real world outside, the issue of IP, its address space, its association, its forced association by default, is actually it's really difficult to start undoing that. And we do have work on progress in using something called RENA to attack that problem. Right, so this is all what's going on with the 20 or 30 people that are in this team at the moment as we speak. So lots of this lots of it's published, huge amount of it's already public and in action or in the develop branch. Right. So you can read as well as I can, but so the idea is that, so one of the problems we've had is that the mathematics we were given in the first place was wonderful. It was proved in its own terms, right? So there was a proof that, a stochastic proof that basically, unless you held 51% of you're going to have 51% of the adversaries, that this system would remain stable over time. But then there were a whole bunch of assumed properties of the universe, like instantaneous error-free global communication was a starting one, that the mathematicians had started with, that when you come to a real-world implementation, you've actually got to start talking about how much can I weaken that assumption without destroying the underlying proof that they've got in the mathematics. The other thing that we've had is, and someone was over lunch. Somebody mentioned, you know, all of these programmers are younger than his children. Right, yes. Right. Well, actually, the core team that originally built this, the peak age was 24. Right? The median age was 22. That had its own problems. They're no longer with us, but that had its own problems in culture, in style, and in all the rest of it. Sorry? No, they're no longer with the company, shall we say. I do believe they do believe that last I heard they're all still alive, but yes. Right. And this whole issue of I don't know how, again, it's an interesting culture, you know, but it's an interesting thought culture, the crypto anarchists, or whatever, however you want to view them, how they view the rest of the world and its institutions. So the whole issue of the inappropriate exercise of eminent domain, i.e. stealing things by the state, or issues of freedom of knowledge, freedom of information, leaking information about transactions and all the rest of it, all are strong in their minds. How the hell do they maximize their ability to remain private and anonymous without stepping over a boundary whereby nation states say you can't use this here, it's illegal to own this object. There's an interesting balance in that process too. Right, and one of the things that we've been doing for the overall is this whole issue of constructing course performance models to do failure modes effects analysis so that we can reason about the performance. Right. So we talked about formal proof today. You can't. It's one of the things that struck me from one of the earlier conversations was this concept that they were working their way up an entirely different tool set, getting more and more formal, and the more you moved up, the more different tools you had to use in order to achieve the outcome you were interested in, and the less people you had to do this. So actually what they were trying to do was they were changing tools and requiring higher, we require better skills, but requiring a very huge breadth of knowledge from those people. We've actually taken the opposite approach here. Right. I don't know how many of you are familiar with Haskell as a programming language, but it's a strongly typed, non-strict functional programming language in which you can write things that are amenable to proof processes. Right. And what's happened is we've been constructing Haskell executable specifications. Yes, they run. They may run like a dog in terms of performance, but that doesn't worry, because what you're doing is you're helping capture the real-world requirements. You're doing that. You're capturing that intentional semantics, and also you're able to start then refine those objects, and then into better data implementations and hence better operational implementations to be able to achieve your performance goals. And what we've been doing is effectively using a piece of, using it on the next slide. Yes, we've been effectively using aspects of category theory to help us solve the problem. Okay, what you're doing here is you are constructing. This doesn't have a button, does it? For that, you're constructing in your more abstract version something that you can believe that's reasonably close to your mathematics. You're constructing a more concrete version, and you give it an abstraction so it can go that way. You then turn around and have operations at this top level. You can then execute your more refined approaches, then move them into the test results, abstract those test results, and check that you've basically gone around the commutative diagram in the right way and end up with the same answers. Right? Now, this is something you can teach programmers to do. Right? You've sort of introduced the category theory is relatively easy to do in that sense. Okay, I've got to move out. Okay, right. So the slides, aren't they? What we have been able to do is this type of stuff: the design, help them with the verification and the validation, and quantify hazards. So it's even getting into the risk register. We're being able to put numbers on this. Right? We are also able to use techniques that we've developed over the years of how things perform, viewing performance as not as something you add to something, viewing performance as a privation, i.e. the removal of something. It takes time to compute. Packets get lost, but you're looking at trying to bound those properties as opposed to make them perform better. I will quickly say that there are formal models, because I'm running out of time, just to do this. And basically, one of the interesting things that the formal models we are using are including the notion of failures. So we're incorporating failures into our performance framework. And we won't bother to do that, because you can find it out if you're interested. Why? Because I know how it's 24 slides, wasn't it? Let's move on. Yes, okay, there I am. Just so I can have some questions. What we have been able to do here is decompose some of these subsystems into composable performance objects. So we can actually reason about these separate components and say, when you glue them together in a long chain, you can actually use compositionality arguments to argue that they behave that way. Not only have we done that arithmetically, but now that we're building the systems and put them in the field and we're measuring them, the correspondence between the mathematics and the reality is extremely good. It turns out that they are good indicators. And what that permits us to talk about and reason about is normal operation. We fully understand how to keep the system running. We can now worry about the exceptions. You know, when there is a mid-Atlantic earthquake and we lose all of the communications to North America and Europe, will the system survive? And the answer is yes. We lost I don't know if you know, but Amazon, Ohio disappeared for half an hour week before last. Basically, we didn't even, it took us 20 minutes to realize there were alarms going off, and it only was, at the time we found out what the problem was, Amazon came back online, and the system just over it. Questions? So. We have taken a mathematical formal model that's on paper. No, the point is the highest abstract model is something that a human being does, typically a page or two, but at such a high level of abstraction that you can convince yourself it's close enough, right? Oh, yeah, that's where you use several people. Agreed, right? Yeah, but the point is, no, a lot of the. Oh, sorry. Yes, so a lot. Yes, there are Isabel and Koch models of a lot of these objects. So once we've got it to that executable specification level, off the paper into something that's high level and abstract, then basically Isabel, Koch, various portions of the process are proved that way. The whole portion is not, because it's just against expectation. You're looking to prove safety and various other things. You're not trying to. You start by we've probably got 75% of the world market, so we're okay. The rest of you may be in real trouble. Absolutely, yes. That was right. Oh yeah, well yeah. Well, oh, it is. It's actually putting on courses around the world and doing this to do this. So it's very it's very open and beneficial in that sense. There's a whole but oh, there's yeah, I was joking about 75%. It's probably only 50. But right. But what I was saying is the market for it turns out now it's getting hard. It's got harder. But the point is, it's a very tight community. So what you do is you persuade half a dozen of the real key players to work for you, and everybody else wants to join them. That was the original strategy.